Hello, ladies and gentlemen. My name is Jerzy Baranowski, and I wanted to welcome you to our second part of lecture on one-parameter uh, models in STAN. And this lecture is also created using the lecture from last year. This was one of my earlier lectures, so I had much less control over time. And if you go back to those earlier videos, they were explicitly long, and this one was supposed to be a very short one, 5-minute example, and it finally ended over an hour. So this is a cut part of that is reduced to an hour and considers the modeling of airline accidents on a known dataset from the 80s, which just gives us the information about the accidents in the US. In this lecture, we consider Poisson distribution, and let's move to that. Poisson distribution. Poisson distribution is a probability distribution of expressing the probability of having a certain number of events that occur in a fixed interval, for example, in a year, in a day, in a week, or in a certain area, if we are considering spatial distribution, and those events occur with a constant mean rate and independently in interval or area. So generally such things can happen in multiple situations. We'll in a moment. What is more or less interesting, probability mass function is maybe less. This is a one parameter model with parameter lambda, and x is our number of events that can occur. So this is a discrete, x is a discrete variable, and what is interesting that mean and variance are both equal to lambda. And because variance is lambda, standard deviation will be a square root of lambda. And this is useful for analyzing models, especially in more complicated cases, because if our data does not show the same result, that both mean and variance are equal, then maybe something else needs to be used than Poisson distribution. However, if they are approximately equal, then it's a good idea to model it with Poisson distribution. And where we can use it? Well, we can use it in many multiple situations, and among the others, those can be numbers of accidents, numbers of that can happen in a city, number of police stoppages of drunken drivers or speeding drivers in certain times. It can be numbers of customers, number of people going to a website in certain time period, or more technical aspects like losing packets during transmission, or other generally discrete events that are not happening in certain constant rate. We've got some multiple of ideas, and we have two of them today to discuss. And we'll start with maybe a little bit morbid question of how likely are you going to die on a plane, or how likely a fatal accident can happen during a flight. And if you know the classic 80s movie Airplane, which is a comedy classic of and parody of multiple airplane scares flights from that period, you know that anything can happen. People can get hysteric, but generally we go to a happy ending, even for autopilot. If you've seen that, you know what I mean. If you didn't, you should, because the ending is something else. Either way, in real life, such hopeful results are not really happening. People sometimes die, and we will look at the actual data from American statistical offices, and from the same period, like the movie, it will be the between 70s and 80s. So what do we have here? We will start again with the we can start with the Jupyter Notebook. I have the an Anaconda environment. As always, I'm not starting with a clean one because I've just tested does my notebook work properly. Either way, we have our airlines fatality problem. So let's we have some. I have some lot of things here, which will be reduced version for later, and what we are really doing here, we will be considering our data set, which is numbers of fatalities from from 1976 to 1985, from Statistical Abstract of the United States, and we'll be trying to create a model that will be able to predict for 1986, which we also have a data, but also we will try to create such model that we will be able to analyze its entirety. We'll be able to analyze how creation of such model occurs, how we are doing it from start to the end. And let's look at our data set. Our data set is a table of 10 rows. Just a quick note, I've hidden some of the more technical non-statistically related Python code. You can see it. You will be able to see it when you will be doing when you will be verifying it later. Either way, of course, if you want to, it will all be on GitHub. What you can do, what we can see here is this is our table, which for each year records the number of fatal accidents, the number of passenger deaths, and something called a death rate. Death rate is the number of passengers dying per 100 million of miles, because planes fly a lot during a year. And from that we can approximate the number of miles flown per year, which we'll be using later by dividing the passenger deaths by the death rate. The original data is available in Gelman's book, but also we'll see it here. The example is one of the exercises from the book. So generally we'll start with the most simple model that's possible. We'll be modeling our accidents with a Poisson distribution with an assumption that number of fatal accidents per year is generally fixed. So independent of the year, we have a constant probability of having having this number of accidents, and we will be trying to find such lambda, such a rate of our events that will be consistent with our data, so that our data will be distributed from this Poisson distribution. So our likelihood will be generally that y is conditional on just on lambda. So we start with the problem of creating such model. If having such model, we have a likelihood directly from the concept model, but we need to assign prior for our one parameter, and today we'll try this one nice technique of fitting certain useful distribution in order to get the parameters to fit our constraints, because we of course can do we can assign fixed constraints for our parameters, but those parameters that such things can be numerically challenging for our computational engine, in this case Stan, because which we will discuss in some the future, Stan really requires us to solve certain differential equations, and differential equations on bounded domains are difficult matters, and to be little precise, there are problems, and generally we want to just avoid the boundaries that we are sure that we are not be going there, and that's why we will try to get some constraints for our lambda. Of course, lambda has to be positive, so this is one of our constraints, which we cannot avoid. So we'll have to do some. We'll have to use the prior distribution with a bounded support of real numbers, but positive real numbers. But what we really are missing is the other end, and really we don't know much. We cannot do a lot of things, especially that we shouldn't really base our prior distribution on the data that we have. We can, however, look at least not on the output data. Maybe we can get some consideration from the covariates that we have, that our independent variables, like miles flown or time, but we shouldn't base it on actual outcomes, because that in such case we would be really using data twice. This can be done in certain situations, especially that we have a little data and we have to do something, but generally we should avoid looking too strong into data. However, what we can say about having a very little knowledge about airline fatalities, we are relatively sure that from even observing TV or on the internet, we don't have daily occurrences of fatal accidents in air flight. They are much rarer. Generally, it is commonly known, or at least it's a common knowledge that, or common opinion, that air flight is the safest way of transportation, because the least number of accidents happen. Just when something happens, a lot of people die at the same time, but actual accidents are very rare. So what we can do? Well, we can start with the assumption that having an accident, one fatal accident on the air flight once per day, or 365 of them in a year, it would be highly unlikely. And that would give us certain bounds on our prior. Of course, we could be even more restrictive, for example, reducing to once per week, but that would be stretching it a bit. We cannot be sure from our uninformed opinion that it is that there's no such accident per week. Per day we can be relatively sure. If it will be once per day, people won't be saying it as a safe method of transportation. So we'll use our standard, our very known idea of having the relationship between standard deviation and confidence interval, that generally mean plus our plus 3 standard deviations give us 99% of distribution. So in this case, assuming that 365 or more should be not more probable than 1%, so that we are being open, we are not giving too restrictive option, but we want to have we want to play it on the safe side, that our distribution will be safe. So general idea is that we need to have lambdas that will be less than this. So lambdas smaller than the value that fits this equation would give us the rate of less than probability of occurring 365 accidents per year would be have a very small probability. So we want to find a probability distribution that will just give lambdas that will be smaller than that. And first of all, let's determine what is the actual value of such lambda, and this is of course a quadratic equation for square root of lambda. We could either do a formal substitution, or we could just when we are interested in the positive result, we'll be doing some rounding. So generally we just use the polyroot function from NumPy, and this polyroot function solves us this equation in order to
determine the square root of lambda, and we take a positive. We take a positive root of these equations and square it, so we would get lambda upper bound. And this lambda upper bound in our case would be 312, which is a number. So what can we do now? Now we should choose a distribution that would give us positive values, and that would assign values above 312 to be 1% probability above equal or above to 312 be less 1% or less. So a good idea, or like a simple idea for our case, would be half normal distribution. Half normal distribution is a generally absolute value of normal, in a sense, absolute value of, this is the variables that are absolute values of values sampled from normal distribution. All other ways, just positive half of the normal distribution, just multiplied by 2 in order to have an integral equal to 1. And this distribution is good for our case because usually, normal distribution has thin tails, so everything large above our 12 will be even smaller because the probability in the far areas of normal distribution is rapidly dropping. So a lot of probability is located in the center, and the farther away the probability is lower. So getting even more accidents would be less and less likely, happening very fast. So half normal distribution for our case would be very nice. And how to choose such parameters of half normal distribution, and we can use it in Stan. This is an option that we could use any kind of equation solving system or numerical optimization system in order to find this, but Stan has one implemented. We can use it. This will be different options of what we can use in Stan, and we will be using Stan algebra solver, which is generally a nonlinear equation solver. And this nonlinear equation solver is documented in Stan documentation, and generally is a Newton method. This is a Newton method for solving equations. Of course, solving nonlinear equations has its own problems of multiple kinds, but really we are not. In our case, we don't need as much precision as. That precision is not really important because generally we will be far away from those tails anyway. And algebra solver can be used in more complicated Stan models. For example, you can have a situation that certain variables are related to each other by a nonlinear equation. And in order to evaluate the probability distribution, you would have to solve this equation. And if it doesn't have an analytical solution, and they don't usually have, you will need to use the you need to use some kind of solver, which will have to be located in Stan in order to get the solutions iteratively in each probability distribution evaluation. So you can use it in many cases. What we'll be doing here, we'll just see how such model looks like, and it's not that complicated, but let's just check how it looks. So we'll have the general idea what's going on. So we are again we have a certain Stan model. I call this prior tune 3 because I was checking multiple distribution before, and the names are not important. In this case, we'll be having we'll need a target function. Target function of our function that will specify our equation. Our equation in this case is that 99% of probability is below. We have the condition of 99% the probability is below 312, or using cumulative distribution function. Really, we are interested in this little part of cumulative distribution function in the end. So we want that the value of cumulative distribution function at our point, which will be 312, will be equal to 1%. And this can be computed using the of course, normal distribution, just normal cumulative distribution function by operator multiplication. What we are actually having here is certain specifics of these functions that can work with stan. So we are defining them in a function block, which has to be a first block in our model, and we have to define a function which will return vectors and take vectors and take certain vectors of values, vectors of parameters to be optimized, and we will need the and certain testing values that will be used in stan. And these functions, this requirement of an API, so it's less readable that will really look like. Either way, we need to compute, especially that you need even for one-dimensional equation, because it's a single-dimensional equation from one parameters and one condition. You need to return a vector from the equation. So generally, we want to fit this distribution. So we have this condition. So this is our equation that probability of lambda being 312 or more is equal to 1, which we can get from conditions on cumulative distribution function. And the thing that might be surprising here, why this is exponent here, because in here we will be certain computation that's happening in the that are happening in our system is really the done on a logarithmic scale, and using such computations, using such logarithms, it will be much easier for us to compute things. There will be less problems in computation, especially in the Gaussian probabilities, because again, everything in Gaussians becomes very, very small, very, very fast. So when you are at logarithms, you are on a much more normal scale. It will be negative numbers, but they will be reasonable ranges. When you exponent them, then they will vanish very fast. So there is a big probability of numerical errors. And what we are here, we have data. So we will supply our model with an initial guess of what in our case sigma of our distribution should be, and we provide the probability that we're interested. So which value has to be above 1%? Why? Because we'll be using this function later in order to turn different distributions for further analysis of our model. So using block of transform data, we'll be able to compute our standard deviation, and we'll be doing it by these diagnostic elements of the function, and we'll be using function algebra solver, which has to be supplied with all those elements of the system. So it will be our distribution from the function block, it will be our initial guess, it will be our value that we are interested in to be not below 15, it will be above theta actually. Will be below theta, and I'll have to correct it later, and those two dummy variables that and this will be print as values, and we'll be generating our quantities will be the sigma that we are interested in. So we'll just getting sigma from our model. And how we do it? We have to compile this model, because again it's we'll need C code to do this computation. Of course, again, we don't have to use it in stan, because we can solve this equation anyway that we want to. But I'm showing this for you because when we will be doing more complicated models that will require to solve certain equations, in order to evaluate the model value, you will have to do something like this. And the model is compiled, so not a problem. And what we are doing here, we'll create some kind of data, and this data will be our value that we want to have 99% of probability less than is our lambda upper bound, which we assign here. Again, because here everywhere we have vectors, We'll also supply it with in the form of number arrays, and we give it initial guess. This initial guess has to be relatively large because we're starting with large numbers, and we are using it in logarithms because later we will need this for our computation. So we are sampling for our data, we provide seed, we provide our data, we use fixed parameters algorithm because our model doesn't have a parameter block, and we have only one iteration because we don't need to repeat it, we just need to compute it once, solve the equation once using algebra solver, and of course one chain because one more, and we get the from our parameters we get sigma, which will be an array, so we'll take a 0 element from this array, and the sigma will be 121. Of course, after certain rounding, which I'm using this rounding, so it will be an easier number to write it instead. But it is really and it doesn't matter. It doesn't matter in case of these tails because there are so large numbers that we don't care. If we have some more specific situation, maybe we would have to be more precise, but not in this case. This case, our prior will be either way. We are still very far from the realistic numbers, so we just have this very weak bound of 365 exponents per year, and like if it's 364 or 366, it really doesn't matter. If it is the 1% probability of higher than that. That's not important. Data will skew us anyway. This is just to avoid some absurd situation of getting very large numbers very fast. So let's see how it looks like. So again, we can plot this our distribution. We are using standard normal distribution and that's why we need to multiply it by 2. So in order to plot it, we just need values, and using this sigma value, as you can see, the probability 100% is here, and this is our tail values. So all above that is 1% probability, circa value. And this is our that's how we tuned our prior. So our prior distribution will be a half normal distribution with sigma of 121. Half normal, so starting at 0, looks like this. Support is 0 to plus infinity, and 99% is located here. So as we did before, we start with doing some prior checks. We are not extending full possibilities of prior checks, but we just need to see if our priors give us something that makes a similarity of sense, that at least our data that we observed can be realized by our prior with not minuscule probability. So like such things can happen in our prior. That is a good starting point that our model is not absurd. If our data would be inconsistent with our prior, then we have problems. Those problems come either with our model, which we probably wrongly implemented. This is our first check. Then, if our model is well implemented, maybe our assumptions were wrong. And if our assumptions were not wrong, then either data is wrong also. But like, there is something called common theorem of I'm mixing the name. I'll check it later. But generally, there's an idea proposed by Professor Gelman that errors are usually fault of the model, and not of the computation and other stuff. But like if the model is wrong, then something's wrong. Then the results are wrong. So we'll be doing prior predictive distribution to see what's going on. So what we'll be doing, we will simulate our we'll create a new model for prior predictive checks. So that's why PPC. It will be the naming conventions in here is airline, fatal accidents, half normal, PPC. So if we use different prior means, of course, you can use your own naming conventions. I'm giving it here, so when you will be seeing my code, you will get some idea what's going on. So our model is again very simple in order to compute these stuff, because it is the our data will be just number of years analyzed, so we'll be able to sample more than one if you want to, and we will be sampling lambda from our half normal distribution, which is what is important here. You can add constraints in stand model at the generated quantities block, but those constraints will not be enforced. So if you put here constraint lower value 0 and you will put normal distribution, then you will get errors. In order to, and first of all, you will get sampled from, you will have negative values that will be given to Poisson distribution, and that will generate samples. So you need to compute absolute value of normal distribution, of samples from normal distributions, which have then this nice option that they are just distributed as a half normal distribution with the same parameters. So depending on how many years we want to simulate, in this case we just take the we are generating the vector of integers, and in a for loop we will be just sampling from probability Poisson distribution with parameter lambda that we sampled before. So having those, of course, like we again can do some we can do some sampling from our model, and we're going to compile our model, and we will do some sampling. We'll just do from one example here, and we will be using the fixed parameters algorithm again, because we have this here. So maybe like I'll just break lines so it will be more visible for you later. We are not using warm up because we are not really doing inference. We're just doing the we are just sampling our model, and we have the we are doing the same the refresh, and we have the we have specified the seed. So we are sampling this our model. We get the sampling block, and of course we can repeat this sampling if we really want to, and we cannot because I haven't run it yet. So let's just run it. Okay. Everything is working, including Shift Enter, which wasn't working last time. Our plot is generated here. As you can see, here is the code for the just make it bigger. As you can see, this is how the algebra solver worked. It just didn't much time. This did this one iteration and gave a standard deviation of 121.126, which is rounded to 121. We read our model, we compiled it, which is stack, and we simulated it. And now it's did everything. And again, this no problem here. 1000 iterations happened instantaneously because we are sampling really from normal distribution, Poisson distribution, so nothing really was interesting was happening, and we get our data. So we are using the extract method. We get from our model, we get our parameters, so lambda and simulated outputs, figures. How does it do? So our lambda parameter is of course consistent with our half normal prior because it was sampled from it. But like this is a check that our data generating model is okay, like not something strange is happening. So this is at the moment it's okay. Prior was generated, so it looks okay. Number of accidents. Here we can see the actual values that happened here. So they were all around 2030, and well, they are located in the most probable area. Their tails are filling the up to 365 accidents. So this is our data is our prior model is consistent with the data. The data are not something that would be impossible to happen in our case. Even like the more likely areas. Of course, our prior could be much more informative, and we could just be limited here, but again, we would need to have some kind of grounds why it was informative. So at the moment we assume our very limited knowledge of airline crashes. Of course, if you would be doing such model for something real, then you would have to get more knowledge in order to get some more prior information about what's going on, and get this knowledge from experts or learn yourself, or get it from other sources. So generally, you would have to need to do something like that. So our prior is okay. We can start doing some kind of modeling, and this kind of modeling we can use by creating appropriate stand model that will be able to infer the value of lambda. So what we are doing here? Here we have the data block, which is now supplemented with actual data of observed values. We added parameter block, which will give us the real the value of lambda, and here we enforce the constraints, so there will be no need for absolute values, especially that we give lambda as distributed as normal. So normal but with constraint, and that will give us the half normal distribution, which we then create our likelihood function that each of our y's of our outputs is distributed with a Poisson distribution with this lambda. So our likelihood will be each of these elements individually, and for extra kicks we just simulate some outputs because we will need it for our prediction for 1986. So we'll just simulate the data here. We could use it only with one, but like I didn't want to change it now. So we'll have more samples of YSIM that's really needed. But we don't care about too much. Generally, there will be marginal distribution for each of those for m number of years with these assumptions of the model. So again, we compile our model. Maybe we'll just do it on the fly here. Just do this again, so it was some strange dependencies. We are having model. Compilation is needed because model is cached. You don't have a cache model in the repository, so you have to compile it yourself. And again, we are using the our data. So we are taking our data from our data frame that was defined above. This data frame was called A-line data. That's why it looks like a nice table, because Jupyter and pandas plot nice tables. So this is actually a data frame, not table. Not like a markdown table. This is just a data frame is nicely visualized by Jupyter. And we are, so m is number of our rows, and y is number are our values of these fatal accidents. This is nice because such presentation, even if that is a pandas series, it is being processed in a way that will be useful for stands. We don't have to convert it too much. And of course, we'll be doing some sampling using our model, using our data with a given seed. Then we extract our parameters, and again we will have a lambda and YSIM. And here a bit more is happening, but like really this problem is very, very fast. As you can see, gradient evaluation took 2.8 times 10 to minus 5 seconds. So 1,000 transitions in our models would take 0.28 seconds, and each of chains in B is being computed approximately around 300 at most 300 of seconds. So very, very, very fast, and our model was sampled and everything. Everybody's happy. We'll just compute some values for later. So we compute mean lambda and our confidence interval for lambda, and it was here that our mean lambda was now 23.92 with a confidence interval of 21.47 to 26.31. And here we have a complicated, very complicated graph sequence, which we'll hold here. You could verify what's going on later. So what do we have here? First of all, in the context of our likelihood and our data, our posterior is much more thinner than our prior. Our prior in realistic aspects is really flat. Our consideration for lambda was like very far away from the data. So our prior was very flat, it was very non-informative. Generally, it's normal distributions with around with sigma around hundreds are very flat. So maybe some scaling is useful for modeling such processes. And let's see our 89% confidence interval for lambda. And as you can see here, it's most of the distribution located here. This distribution is kind of normal in its shape, or like bell-shaped either way. It's symmetric distribution, so you can see what's going on here. How the values are distributed. Most of the values are between those. 89% are here. Of course, we are using normal histograms. And our numbers of accidents, well, this is not that good to be like. Of course, our data are consistent with what's going on, but as you can see, they are very spread in these confidence intervals. So really, well, of course, they were differing by itself, but what's going on here is that our model is not very well corresponding to our original data. Our original data are possible in it, but not is what those dots represent is where these what was the value of accidents in a certain year, and if there are more than one here, it means just that the same number happened in the same year. So using this model for prediction, we have sampled even too many samples of posterior predicted distribution. So we have these predicted values of y, so we just need to compute the appropriate values, and we can use it by computing a median of it and having the again highest posterior density interval, and as you can see here, mean number of predicted accidents will be 24, median. Sorry, median of predicted accidents is 24, and our confidence interval is wide. As you can see, while the median is relatively okay, because in our prediction there were 22 fatal accidents with in 86, but we have large uncertainty about that. So maybe getting something. So maybe this is the too simple model, and this model is very simple because this model says us that whatever happens, the rate of accidents is constant. But looking from our data, the miles flown are not. Year after year, we fly more, with exception of 82. But generally, each year after year, the number of miles flown by a plane was rising in the period. The Flygscam concept of Scandinavia was not even in place yet. This is, if you haven't heard of it, it's a special word for a shame of having to fly, and flying, of course, is unecological and loses a lot of resources. So let's consider a better model that at least considers the numbers of flights per year or miles. So we can reformulate our rate in Poisson distribution, lambda, as an product of intensity, so how probable is aspect, with relation to exposure. Exposure is, so like, for example, how large a dosage in response how to this dose is the for example, it will be deaths from certain poison. The more the poison is given to the populace, then the intensity will divide how it's effective in killing the populace. In our case, the exposure will be, of course, number of miles flown, because the more you fly, the less likely you would die. Maybe that sounded wrong. Either way, we want to estimate the intensity. So now our model is still one parameter, the parameter intensity, but for each of the years, we will have different rates, because those rates will be proportional to our intensity and to our exposure, which we have in our data. So we are creating more complicated model, still one parameter model, but this model might be able to handle our data better, so give us better predictions. And again, we will need new prior. We still don't know much, because we shouldn't use our data before, and we haven't acquired new expert knowledge. So we will be doing the we'll assign the prior in the same way, but in this case, instead of lambda, we will use this product of theta and n bar. And n bar is a mean of miles flown. So we have some kind of estimate that in average, if we have an average amount of miles, our exposure will not give us the 365 accidents per day. As I said before, because this is very uninformative, it's not that important in this case. So we'll just do the same situation. Again, we'll compute the mean number of miles, and we'll solve set up necessary polynomial equation, which is here, and just scaled by mean miles here, so it will be computed nicer. And so we have a unity with theta. We compute again root of theta. We are not rounding anymore because of we are much lower than 1 with our values, and our theta upper bound will be 0.055, which actually is a much longer number, but what we need here is what we are doing here is like just to give it some kind of visibility. And again, it's not that important, so we'll just keep it to 3 numbers before. And we'll again use our tuning function, because again we'll be assigning half normal distribution, but instead of for lambda, we assign it for theta, so it will be much thinner half normal distribution, because our scale of parameters will be much lower. So generally, everything is relatively clear still, and our model. Then what we needed to change, we need to change the starting point, because we are arriving in different areas of probability distribution of sigma, and all Newton methods require good starting points, especially in this case. We are in logarithm, we're in the small values. There will be some issues. We assign theta upper bound, we call the same function, which is again computed very fast, because we are just solving a one-dimensional equation with a Newton method, which is absolutely fast generally. So it takes us around 10 to minus 5 seconds, so very small, like 3.37 microseconds. So very fast, and probably most of that was the handling of the printing statements. So this is what we've done here, and again we can compare how our probability distribution looks like, and it looks similar, but the scale is different. So again, it's a half normal distribution, but for values of theta around 0.55 is like this. So everything looks relatively nice. Actually, we could do it nicer. I should edit it out, but I really don't. It's not that important. Just look a bit nicer. And as you can see, so this is the. Well, we are just using the rounded value from here, and. Having this, we can now do probability distribution. And here, our model becomes a little bit more complicated. Maybe even not that much complicated, but we will need to use the create our model from what's going on. So again, the data is the same. no, the data is not the same because we're doing prior predictive distribution, and with our prior predictive distribution, we now need to incorporate miles. And so our data includes the miles, and again, number of years analyzed. So for each of the years, we'll assign a certain number of miles, and we will be generating our quantities in a way that, again, we will sample theta, now theta, not lambda, from this normal half normal distribution with sigma of 0.021, and we will be sampling our simulated values from Poisson distribution with a rate of theta times the number of miles. So generally we have some kind of Poisson regression here, and this of course happens, and compilation is not an issue, and we can sample it again very fast, not much going on, because again this is a simple program. And we will now plot some things from what we wanted, and we have now let's focus on the distribution of theta. Why? Because now we will have to consider each of years separately, so we will not fit it in one figure. Here we have our half normal distribution. Again, this everything is consistent. Nothing was failed. Our sampling was okay. We've generated what we wanted to generate, and our theta is half normally distributed with required parameters. Now let's look at our simulated outputs. We resampled for each of the years separately, as we can see, it is of course consistent with our previous before, and our data is consistent with what's going on, that it's possible or even around the around maximum value that we wanted. So everything is now it's okay. Of course, as you can see, those scales might be differing a bit for the from year to year. At X scales here, maybe it would look better if we just add share X. I'm just specifying the plot so it may be clear. Okay, now we have everything in the same scale, and all those ticks are 365, and as you can see, everything looks very similar, and really our values are, it looks terrible because I've hidden the true values. So let's go back to the previous one. So as you can see, true values are happening where they should be happening. So everything, at least on the prior scale, looks okay. Like this, our prior distributions are not conflicting with our data, which was what we wanted. So let's start with the actual inference and seeing how our posterior predicts our actual data. So our model, which will be very similar as before to our previously used model for inference. This time we've added miles to it, so the name is appropriately changed, and we've adding the vector of miles, parameters theta. Our model computes the rates in the Poisson distribution, and our generated quantities are even here that we are sampling again for each of those years. So we'll be able to do the posterior predictive checks how it looks like in comparison to what we wanted. Okay, so model is here. As you can see, it's open. Compilation not needed. We are providing you again data structure constructed from our data frame. So we created a dictionary of number of rows, column of miles, column of fatal accidents. We're doing the fit with let's see, we are extracting the parameters. Let's compute the necessary values. So we have the both mean theta and its confidence interval, which is given here, and we create again a nice plot of what's going on here. And this nice plot is we have very similar situation as before, but on different scale. So our lambda is again very thin in comparison to the prior, which was very wide, and our highest probability density distribution is here. And again, it's kind of centered, kind of similar, a bit more skewed maybe, but like this is something that will require further investigation than we want to do here. And let's do our histograms. And those histograms are, again, they are not that good results that we want. Of course, all our data happened here and are within the distribution, but there is certain effect that we can observe here, that for earlier years our model was underestimating the amount of data, the amount of accidents. So they are happening in the tail values. On the other hand, when we are approaching the 80s, now our model was, except of 1 year, 1982, which had, as we observed, less flights than a year before, it was underestimating all of the. It was actually a funny year because we, as you can see, we had less flights, but more accidents. So this was something that would require certain investigation. What's happening here, because this is something that's giving like a certain strange behavior. Of course, it's not like substantial difference number of accidents, but like less flights, more accidents. So maybe looking what's going on, like what was the reason for that. Maybe we should, if we return to this model later, maybe we should need to consider something, what's going on. And again, what we are having here, except of 1982, after 80, our model was overestimating the number of accidents. So something is happening here which our model cannot capture, but it allowed us to identify that despite controlling for the number of miles flown, there is some effect that's here. Either at first we have more accidents than with less number of miles, and the more flights are going, the number of accidents is relatively smaller. So this is something that will require further investigation, and we will return to it in a lecture or two to see how it's going. But let's see how our model works for the prediction. And in order to do so, we will need to compute the number of miles from the data we have. We had a data for 1986, which was just not in our table. There were 22 fatal accidents with 546 passenger deaths and the death rates of 0.06 per 100 million miles. And we can compute miles from that. And we will be we need to create a new model, because our previous models were using our data for years before. So we need to use a model that will be able to estimate our value that we are interested in, because we are not interested. We need to get the value from that. So what we are having here is we are using the same model as before, but we've changed the generated quantities element of y in 1986. We just give the hard-coded value of 9,100 miles. We could do it multiple ways to do it. Even we could encode it prediction for 1986 as a missing data, but then our model would stop being a one-parameter model, and this is not what we wanted here. And we just do the we have created this new model. We compile it, but it's compiled, and we again perform the inference, which was again very, very fast. So not much to do, not much to discuss here. And we have now can do some prediction, and as we can see, the mean, again, so here's the mean, so it's a median. Median of predicted the accident deaths is 38, which is much more than really happened. And again, the systematic effect that we've observed here is even more flights, and again, the number of accidents is much lower. So this is something, the seasonal effect or the time effect of that is happening. This is something that we would need to model and see what is going on, and we will do it in the next lecture. And so as you can see, we have started with very simple model, which haven't told us much, except that we had a lot of uncertainty for our predictions. While we got the actual prediction wasn't that bad, the one we got before, we see that there's something more in the data. We've started doing the more complicated model that should work better. Actually, it gave us information that something is happening in this data, that if we want to reduce the inference, we have to model more. We have to create a more complicated model to extract additional information.
Thank you for listening to this part of the lecture. As you can see, we've covered the topics of prior predicted distributions, posterior predicted distributions. We've considered different types of priors for one parameter in the discrete model based on Poisson distribution. So we've considered the integer number of cases that can occur during each year, and from this lecture you should be able to remember these basic concepts, how to simulate discrete events and analyze them. And from this lecture we'll move to another simpler topic in the next video, which will consider cancer modeling. Thank you, and see you next time.